Hello, in this video we are solving B section 2 of our free response, where we were asking what is the strength of the electric field right here in the center of this arrangement of charges, so at this one point. The first thing we want to think about is conceptually, what would the electric field lines look like due to each one of those charges? Well, we have our positive charge Q in the upper left. We know that electric field lines always go away from positive and towards negative. So if we were just looking at positive by itself, at about this point, it would be pointing to the bottom right. Due to just this minus Q charge up there, it would be pointing towards that charge as well. Due to the minus Q charge down here in the bottom right, well, that's yet again another electric field vector pointing in that direction. And for this positive Q down here, we would have a vector pointing away. So we end up with 4 vectors. These two are added together in the same direction as well as these two. And we have a 90-degree angle between them. So our resultant, which would look something like this, would have an angle between the vectors and the resultant of about 45 degrees. So let's figure out now what would be the strength of the electric field. The electric field at any arbitrary distance r away from a point charge Q is given by K times Q divided by r squared. This is going to give you the magnitude of one of those small vectors that we drew previously. So if we look at our one basic triangle that we created, we had a vector going up in this direction. We ended up looking for something along here, and we had an angle theta between those two. Well, what we've done is create a small triangle. This part that we're interested in down here is adjacent to the angle, and the part along the top is going to be our hypotenuse. So if we know that each one of these small vectors is made up of a strength of kq over r squared, we know that this entire hypotenuse right here would be twice that. So 2kq over r squared. The trigonometric identity that relates hypotenuse to adjacent is going to be cosine. So if you recall, cosine theta equals adjacent over hypotenuse. So solving for adjacent, we simply multiply cosine theta by hypotenuse. So here we would have our hypotenuse, 2kq, divided by r squared, multiplied by cosine 45, which equals adjacent. Now this is only the contribution and the rightwards pointing direction from these two vectors. You got to remember that we also have 2 more on the bottom. So we're actually going to double our answer right up here and call that 4kq cosine 45 divided by r squared. And that will equal the strength of our electric field. We're not quite done yet though, because we've been talking about distances being r. That's just an arbitrary distance from one place in space back to the charge. The only distances that we're given are the distance from charge to charge, which is called s. So we need to use a little bit of geometry to figure out how to express r in terms of s. Our distance right here from one charge to the very center of the square is our distance r. We can find the entire diagonal right here, though, using Pythagoras' theorem. So then all we need to do is cut that distance in half. So if you remember, for a triangle, it's a squared plus b squared equals c squared. So interpreting that for our diagram, we would say s squared plus s squared equals the length of that hypotenuse. So we'll just call this h for now. So we would say s squared plus s squared equals h squared, which means 2s squared equals h squared. Solving for h by taking the square root of both sides gives you square root of 2 times s equals h. Now r is only half of h, so we need to divide by 2. So let's just take h divided by 2, and that will equal r. We can plug this into our equation. In our equation, though, we don't just need r, we need r squared. So let's take the square of both sides really quickly and then put that into our equation. This would mean that r squared would equal 2s squared divided by 4, because we squared every one of the terms in that fraction. 2 divided by 4, we can pretty that up a little bit by simplifying and just simply call that s squared divided by 2. So when we go and put that back into 4kq over r squared times cosine 45, if you remember our previous expression, we said E equals 4kq cosine 45 divided by r squared. Well, this is essentially multiplied by 1 over r squared, which means we invert that fraction. So now we're going to have 2 on the top times 4, and then kq cosine 45 divided by s squared. The 4 and the 2, of course, we can just get rid of this and make that an 8. And if you want to simplify it a little more, recall that cosine of 45 is square root of 2 divided by 2. Plugging that in, our final expression could be E equals 4 times the square root of 2 kq divided by s squared. If you have any questions about the solution, feel free to email me or come by personally.